Thanks so much for the opportunity, and good afternoon, everyone. The topic of my presentation is the evaluation of in-service reinforced concrete box culvert through a combination of diagnostic load testing and refined analysis. I'm presenting today on behalf of my co-authors on this paper, Christopher Gens and Andrew Foden from WSP, my colleagues, and Binyam Aragawi from TxDOT, who was actually the client and PM on this project. Just an overview of the presentation today. We're going to go through introduction, some background material, methodology that we use, the details of our load testing and computational modeling, and how we use those to come up with the refined load rating for these culverts. A little background on the project. TxDOT has over 19,000 bridge class culverts in their inventory, and they are classified as either single or multi-cell box culvert that can carry traffic, and they have a total clear opening of greater than 20 feet, including the thickness of the interior walls. They are part of the NBIS. They receive inspection on routine basis, and Texas has used assigned load rating in the past for these culverts. According to the AASHTO specification and requirements, we can use assigned load rating on the structures when the plans are available with indicated design loads. There's no need to perform load rating based on inspector determination, and none of the principal structural components of that particular structure has a condition rating of 5 or below, or better say the moderate deterioration. However, FHWA, they changed their requirements recently, and they said you can only use assigned rating for in-surface structures if they are designed or checked using LFD and LRFD. Well, TxDOT used a level of stress design, or ASD, up until 1990s, late 1990s, for majority of these culverts, and that causes the main challenge and issue with these culverts. They wanted to keep these culverts still open to traffic. So they selected 1,600 of those bridge class culverts. They performed load rating analysis using their in-house software called CulverT. And load rating results for some of these culverts indicated the need for posting, where these culverts have been in service for many years, subjected to unrestricted traffic throughout their service life. They had no major sign of de-stress or deterioration. In fact, some of the analysis results in the past showed that some of the culverts are filling on their own dead load, which obviously not the case. So it was evident that some level of conservatism were involved in that previous analysis, and we suspected that could be related to the equations that were used for the live load distribution in those models, and they're usually based on the AASHTO specification. Those equations are typically just based on one parameter, fill height, and they are known to be conservative on the conservative side. That's the whole story behind this project. And we got this project from TxDOT, and the methodology behind it is to use a multi-step process to refine the ratings of a select group of culverts within these bridge class culverts. About 40 plus culverts were assigned to us, and our methodology involved diagnostic load testing on a population of 10 out of these 40 plus culverts, and then perform refined analysis on all of them to refine their ratings. Gets to diagnostic load testing. As I said, we selected 10 culverts, and the goal was to understand the structural performance and the response and the load distribution behavior in these structures. So for selection of those, we had our own criteria. We'll look first at different attributes that could have potential impact on the performance of these culverts. Say the fill height, or the culvert geometry, or the location of the culvert, because that could affect the salt property around the culvert. We also look into the previous load rating results, and in terms of controlling rating, the failure mechanism, and the controlling section. We try to select these 10 culverts for the attributes and the previous load rating results to kind of have a wide range over all of these parameters that we considered. Also, most of these culverts out of these 10 were recommended for load posting based on the previous load rating analysis. You can see some of the key attributes of the selected culverts that we chose for the diagnostic load testing. As far as instrumentation, we used a combination of strain gauges and displacement sensors to have a better understanding and better data collection of our 10 tested culverts. For the strain gauges, we use gauge extensions in order to make sure that we don't have any local effects because of the concrete property, non-homogeneous composition, or surface cracks or large aggregates affecting our data collected from the field. As far as the instrumentation plan, we tend to keep the same instrumentation plan overall for all the 10 tested culverts. The plan was to instrument one exterior cell and one interior cell at 2 sections that are 6 feet apart. So you can see section A was relatively heavily instrumented, and it was intended to collect the maximum structural response relatively close to the application of the load. And section B, 6 feet apart, was planned to collect that distribution behavior or distribution response. As far as testing procedure, again, similar testing procedure was considered for all tested culverts. You use triaxle dump trucks, which were weighted and measured before each test. As far as test configuration, we had 5, as you can see in this figure, 5 test configuration. For test 1, we kind of line up the truck with the instrumented sections. And test 2 to test 4, we kind of move the truck sideways to better capture that distribution throughout those 2 sections that we instrumented. And test 5 was for us to just have some collected data on the 2-lane loading scenario on these culverts. For all of these tests, we performed the test at the crawling speed, kind of a static test. We repeated each test 3 times to make sure that the data, the responses are reproducible, and we monitored the collection of the data during the test. If there was any anomaly or unpredicted behavior was observed, we stopped the test when we started over. These are some representative responses or data we got from our load test. On the left, you can see the deflection on the top slab for the interior and exterior cells on one of the culverts. 2 sections, section A and section B, 6 feet apart. And on the right, you can see the strain distribution between the wall and the slab. These are the maximum responses collected from each of the strain gauges attached at the corresponding locations. The second phase, the second part of this project was the computational modeling or the finite element modeling for refined analysis. Again, the goal here was to, number one, leverage our modeling to supplement the load testing program to help us have a better understanding of load distribution behavior in these culverts. And number two, use and leverage these models to perform a refined analysis and get a more realistic rating factors for these culverts. So we started with a 2D model, which consists of a 1-foot strip of the culvert based on a typical practice and recommended by the TxDOT. But we also included the solid structure interaction using plate elements around it. As you can see on the right side of the screen, again, we used beam elements for the culverts. We used plate element for the soil around it. We used elastic links to model the interaction. We also included the beam elements to model the pavement because our load test results showed that pavement and stiffness could have major impact on the distribution of the live loads in these culverts. In order to define the boundary of the soil to be modeled in these 2D models, the pattern, the density of the mesh, we perform a mesh sensitivity analysis. The goal was to optimize our mesh in order to make that balance between the efficiency of the model and our analytical effort and the accuracy of the results. Initially, we used the material properties or attributes based on plans or previous ratings, and we changed that later on during the process based on calibration, which we get to it later on in the next few slides. Initially, we also performed the analysis on the dead load and live load for these, and we look into several parameters, including, for example, a deflection pattern, just as a sanity check, make sure that the model is acting the way that we expected it to be. Then the next type of modeling or level of modeling was the 3D modeling to create the full 3D representation of these culverts and use that 3D model basically for our calibration, comparison to the load test results and do a calibration. We use the mesh pattern that was already optimized in our 2D models and as a cross section, and then we extruded that mesh throughout the lens to create that full geometry. Obviously, when you go to the 3D model, we had to use different type of elements. For instance, we had to switch from plate elements to 3D brick elements or solid elements to model that soil around the culvert. Now we had to use plate elements for the culvert and the pavement, but the interaction part was still modeled through those links. And all of these models were created in LARSA 4D. Again, the attributes, the initial attributes for the preliminary analysis was taken from the previous ratings or the plans, but we changed those properties as we're going to talk about during the calibration process. Again, as a sanity check, you can see the model was analyzed. This representative model of one of the culverts was analyzed under dead load and live load, and you can see the deflection pattern on these specific model. Then moving on to the calibration. So the goal here was to make sure that the 3D model that we created, we can have that model to mimic the results that we got from the test. So what we actually modeled the similar truck with the same configuration, with the same loads on the, like as far as the axle weight, and we run it using influence surface analysis on the models. And we started changing different attributes in the model as far as the boundary conditions and material properties for different components within a reasonable range of those materials that we expected to be accurate. And we did this in an iterative way until we get a closest possible match, a reasonable match between the response out of the model, both deflection and strain distribution, and the data we got from the test. Here in the graph down below shows the iteration process between different models. For example, for this case, you have to go to model 15 in order to get a good match between the test result, and have to do the iteration until we converge basically to the test result. So once we have a 3D model calibrated, it is expected that that 3D model is the best representation of the actual behavior of the system in service. But use of 3D analysis and 3D model is not the most efficient way to perform load rating on these culverts. The common practice is to use 2D models. Number one, because these models take time to create. Number two, takes a lot of time to analyze and post-process, and converting all the plate stresses into effective moments and shear for load rating analysis. However, when you come to the 2D models, then there's a concern. There is that conservatism that is involved with the AASHTO equation to transfer or transition the actual three-dimensional behavior into the two-dimensional behavior. And we believe that caused conservatism in the previous rating in the first place. So we came up with this idea of defining a term called 2D calibration factors, basically by leveraging our load test results. So what we did was we created a series of 2D models with the same modeling procedure as I explained before for all of these tested culverts. We put the attributes on those as the attributes that we already calibrated in our 3D models, and we analyzed them under the same level of loads that we use for the 3D model and the load test. Then we compared the deflection response from the load test to these 2D models with the calibrated attributes, and we kind of plotted that ratio for both exterior and interior on all of these 10 culverts versus the fill height or the fill depth. And we came up with this line that is somehow conservative, and it's on the upper bound of all of these points or dots or responses. And we came up with this equation that is basically a function of fill height, and that shows the distribution. But using that equation, we can apply that to the full amount of load or the demands in the 2D model, and that's basically mimicking the actual three-dimensional behavior. However, in order to make sure that you're not losing any aspect of the three-dimensionality and the actual distribution of the loads, we did also another phase, which was 2D, 3D correlation study. So basically, the goal was to make sure that we achieve a reasonable agreement between the deflection response that we collected in the field, we predicted with the 3D models, calibrated 3D models, and also the 2D models, having the calibrated attributes plus the 2D calibration factor. So out of 10, we selected 3 culverts with different fill heights, no fill, 2 feet of fill, and the 7 foot of fill. And as you can see, we did perform this comparison. Across the board, deflections out of the test and the 2 different models in the 2D and 3D environment, they're very close to each other. One pattern that you can see is as you get to the higher fills, your 2D response would be a little bit on the higher side compared to the test, which is on the conservative side. And we are okay with that. Plus, we didn't have major problem with the low rating of the culverts with the high fill, because when you get to the higher fills, you usually tend to distribute the live loads very well across the length of the culverts. So you don't usually encounter low ratings. It's usually the culverts with the shallower fill or no fill that have problems as far as low rating under the different type of legal and design vehicles. So now that we have our 2D models calibrated, 3D models calibrated, we have those attributes, we have a 2D calibration factor. We created the 2D models for all the 40+ culverts that we had. And we used those 2D models to create the load demands for us under dead load and live loads. As far as capacity calculations and the load rating analysis itself, we followed LFR or LFT methodology based on AASHTO MBE. We had to do all of those calculations as a post-processing in a series of custom Excel spreadsheets. Applicable factors such as load factor, impact factor, multiple presence, or like I think they call it intensity reduction factor in the LFD code. They're all defined based on the AASHTO equations inside our custom spreadsheet for load rating analysis. It gets to the analysis, we use the multi-step elastic analysis to capture progressive hinging. So stage one, we perform the initial load rating by assuming the flexural fixities 100% between all the walls and slab. They're all capable of transferring moments to each other. If you get a low rating at the operating level for any of the design or legal vehicle, then we went into stage two and we place plastic hinges at the location that there is no reinforcement per plans, or the reinforcement has no enough development to provide that desired capacity. And then we redo the analysis. If we still get the rating below 1 at the operating level, we place the plastic hinge or release the moment at the location that had the lowest rating or caused the low rating. So placing these plastic hinges or releasing moment allowed us to redistribute the load. It doesn't mean that the culvert failed at that point, just mean that section reaches capacity and then redistribute the load because of the excessive cracking to the other locations. While doing that, we were very careful to watch and monitor the overall stability of the model. First of all, we never put a hinge in the middle of the slab because that will cause instant instability. It's always placed at the corners. And number two, when we're placing the hinges, we were monitoring the state of stresses in those plate elements and also the level of forces in those links that are providing the structured solid interaction. Make sure that none of those goes into tension. So the stages were basically intended to simulate the progression of the load redistribution along different components of the culverts. And I should mention that we did not have to use all 3 stages for all the culverts. In some cases, we had to go to stage 3 to get the realistic load rating. So here are some representative results out of the refined ratings that we got out of our analysis procedure. You can see across the board, we were able to increase the ratings. These are just for HS20, inventory and operating. In some cases, the improvement was significant, and those are usually the culverts that have a higher fill height on top because they tend to have better distribution. Looking at the results and all the procedure, we are very confident in the procedure that we had and the result that we got because majority of these culverts, especially within this select group of 40 plus that were assigned to us, were close to interstate or on interstate system, and they have seen and experienced the same level of loads as the SHVs or emergency vehicles in the past during their service life. And yet the recent inspection reports and photos doesn't show any significant deterioration or de-stress, and they've been in service without any problem for their entire service life. So just getting to the summary and conclusion, the project focused on refinement of the load rating of an inventory of in-service bridge class culvert in Texas. They were designed and constructed prior to 1999 using allowable stress design method. Majority of them, as I said, have been carrying unrestricted traffic for many years without any sign of de-stress, and some of them received low rating in the past in the previous load rating analysis. The project that we conducted included a multi-step process that involved both load testing and refined analysis to have a better understanding of the actual in-service performance and load distribution behavior. And we came up with the refined analytical approach to refine the ratings of these and potentially avoid posting on these culverts. Again, a select group of culverts were tested. We used 3D Finite Element for the calibration of the attributes. Also, we used 2D models with the calibrated attributes to come up with the refined ratings and use a multi-step linear elastic analysis for the refinement of the ratings. That's all I had. Thanks so much for the attention. I'd be happy to take questions at this point.
Thank you, Amir. Very informative and very comprehensive study. So there is one from Will Shekarachi. Let me read the question to you, Amir. The analysis seems like it was predominantly done on the load distribution though it seems like low rating of culverts is an issue due to lack of as-built plans, sets, and material properties. Did the culverts evaluated in this study have as-built plans? And does the study indicate that Culvert, which is a software, is over-conservative?
Majority of the culverts that we had, yes, we had the plans. That's how we got the information as far as the reinforcement and the material properties for our capacity calculations. There are some instances that you may not have plans, and that's a different scenario. That's a different story. We're not claiming that the culvert necessarily is over-conservative. It's just that it uses the AASHTO equations that can be conservative for some culverts with some geometries. It's not only the fact that the equation in the AASHTO is using basically the fill height as the major contributor in the load distribution behavior. What we found in this study based on our load test is it's not only the fill height, but a suite of attributes. There's the askew angle, the geometry of the culvert, the soil properties. They're all playing a role in that load distribution characteristics. So we tried with using that 2D calibration factor equation, we tried to bring those all in to have a better understanding of what's going on as far as how loads are being distributed.
So since you mentioned skew, that the second question relates to that. The question is very common not to have the culvert alignment perpendicular to the roadway due to various reasons. Have you investigated the applicability of your results for skewed culverts?
Yes. So as I mentioned, when we selected those 10 culverts for our test, one of the attributes was the skew angle. So a few, I guess, out of the 10, maybe 2 or 3 culverts that we tested were skewed culverts. So the results that we had from those skewed were also involved in the derivation of those 2D calibration factors.
Okay. What was the angle of the skew? Do you remember?
It was as probably low as 10 degrees up to 30 degrees, if I remember correctly.
Okay. I have one question, which was we have been looking at culverts in the North Texas area. So we saw some of the culverts have significant scour under the bottom slab. Although the bottom slab is quite stiff, did you encounter that, or did you address that in your evaluations?
We did not consider that one. We didn't have any special information from the inspection on any of these culverts that have a particular issue with the scour. Otherwise, we could have done something with the element stiffness, modeling the soil underneath.
Okay, good. Okay, thank you, Amir. I appreciate it very much.
Thank you very much.
Thank you.